Hello everyone, welcome back to the course Financial Mathematics for Actuaries. In this week, we are learning the bond management or the bond risk management, in which we have already understood the Macaulay duration and the modified duration. Okay, and we have understood that the Macaulay duration and the modified duration actually the rate of change of bond price due to the rate of change in the interest rate or the yield. So today we are extending our learning and we are going to learn something important and what is known as convexity. But before that, we will also understand what is the duration for the price corrections. How to compute the duration if there is a price corrections, and then we will learn what is convexity and how it will help us in bond risk management. So let us first understand the duration for price correction. For this purpose, let us denote the PI as the price of the bond when the yield to maturity is I, and when the rate of interest change to, let's say, I plus del I, the bond price is revised to P of I plus del I. While the bond price can be recalculated at the rate of interest, that is I plus del I, using our price formula, and approximation is also available using the Macaulay duration and the modified duration what we have learned in the previous session. That for the continuous function fx with the first and second order derivative, the function evaluated at x plus del x, that is f of x plus del x, can be approximated by a Taylor expansion, and therefore let us rewrite the Taylor expansion in this way, which is f of x plus del x, which is approximately equal to f of x plus the first derivative of x time del x plus the half of the second derivative of fx multiplied by del x square, right. This is the Taylor expansion with first and second order derivative, right. So using this for our price or the bond price, that is P of I plus del I, this is the same as this, right. So I plus del x, the same way we have written it here for P. Now we will proceed. Okay. So using the Taylor expansion of two first order derivative, we can rewrite the price function as P of I plus del I, which is approximately equal to Pi plus the derivative of Pi with respect to I time del I, okay, which can be again calculated as just, which can be rewritten this as Pi, okay, taking out, then we will have 1 minus 1 upon Pi dPi, okay, upon di time del I, so that we can simply have here like Pi minus, here we will have Pi upon Pi, so we will get like Pi upon Pi is equal to 1, and therefore like we will get the exact same equation here, right. Then okay, we can write, remember that this, okay, I have just highlighted in a different font that this one is basically nothing but our modified duration d star or demodified, and therefore this can be rewritten as Pi time 1 minus demodified delta I, okay. So we can use the modified duration to obtain a first order linear approximation to the varied bond price with respect to a change in the rate of interest. So just proceed to understand what is convexity. Okay. Remember that in computation of duration we use the first derivative, okay, while in computation of convexity we will use both first derivative and second derivative, in fact second derivative. Okay, do it from the beginning. So, to obtain a better approximation for the bond price, we use the Taylor approximation as this. So, P of I plus del I, okay, is approximated to Pi plus the first derivative of Pi with respect to I, okay, plus half of the second derivative of Pi with respect to I time del I square. Okay. So, now we can rewrite this as the same way what we have done, like we can rewrite this into this, that is take Pi out, and therefore we will have 1 minus, okay, minus 1 upon Pi, okay, time the first derivative of Pi with respect to I time del I plus 1 upon 2 Pi, okay, the second derivative of Pi, okay, multiplied by del I square. Okay. So, now here also you can see I have already explained you this term, but here simply Pi upon Pi will get exactly 1 upon 2. So, this right hand side term is exactly equivalent with this. So, we can now define the convexity as the second derivative of the price changes. Okay. So, C is equal to 1 upon Pi, okay, d2 Pi with respect to di square, right. So, having defining this, okay, we can now substitute this in our equation later. Okay. So, let us now proceed. So, using this C is equal to 1 upon Pi d2 Pi upon di square, we have P of I plus del I is equal to Pi, okay, time 1 minus the modified duration time del I plus half of the C time del I square. Okay, when we define C in this way, right, we can rewrite the like previous formula as the present formula here. Okay. So, for the investment with the given, or for the investment with price is given as the way we have already understood, okay, P is equal to sum of present value of the cash flow, okay, where the present value of cash flow is computed as Ct upon 1 plus I to the power t. We can now have, okay, the second derivative of Pi, that is with respect to I, can be written as, therefore, summation of t plus 1 t Ct, okay, upon 1 plus I to the power t plus 2, okay, that is the second derivative of this thing. Now, using this in our equation here, we can, okay, so the convexity now can be defined as, okay, C is equal to 1 upon Pi d2 Pi, okay, upon di square, that is the same thing here we have rewritten again. So, now, okay, while this, therefore, now we have already understood that d square Pi, okay, by di square can be rewritten as sum of t plus 1 t Ct divided by 1 plus I to the power t plus 2, and therefore, C can be written as 1 upon Pi multiplied by this term, okay, or just multiply this, that is t with this t plus 1, and then you can rewrite that this equation can be 1 upon pi multiplied by sum of t square plus t Ct, okay, divided by 1 plus I to the power t multiplied by 1 plus I to the power 2. Okay, so that I have written it here the same way. So it can be equal to 1 upon pi multiplied by sum of t square plus t Ct divided by 1 plus I to the power t multiplied by 1 plus I to the power 2. Okay, or we can rewrite this as, take this in the beginning here, so that we will have 1 upon pi 1 plus I square multiplied by sum of t square plus t Ct divided by 1 plus I to the power t. So this is the formula for convexity. Okay, or this formula can also be written as, okay, like the same way. Okay, this one and this one are exactly same. I have just only separated this so that this will be like the present value of in Ct. Okay, or we can have, right, 1 upon pi time 1 plus I square multiplied by sum of t square plus t time present value of the cash flow in the future. Okay, so this is the formula for the convexity, right? Understand this convexity in a very simple way. We can also rewrite the same formula, okay, by considering these 3 steps. Okay, so simple way we will see, we know that the price of the bond is P is equal to summation of Ct upon 1 plus I to the power t. This is how we will compute the price of the bond, right? Okay, so now once you compute the price of the bond, we will take the first derivative, okay, which will give us the duration, okay, or the modified duration. Okay, so the first derivative will give us the duration. Okay, it will give us the sensitivity of the price, okay, due to the change in the interest rate or change in the yield, okay, which can be written as dp with respect to I, that is change in price with respect to change in I can be computed as, and we know that there is an inverse relationship between price and yield, so we will put it here negative, okay, and therefore dp by di is equal to minus summation of t times Ct divided by 1 plus I to the power t plus 1. Okay, and its second derivative therefore will give us the convexity. So we will take the second derivative here, that is d2p by di square. Okay, so d2p by di square, which can be again written as minus of summation of t time t plus 1 times Ct divided by 1 plus I to the power t plus 2. Okay, so this is the first derivative of p. Okay, this is the first derivative of this, and this is the second derivative of this. So this will give us the duration, while this is give us the convexity. Okay, so now now the final formula therefore, okay, will become C is equal to 1 upon p d2p by di square is equal to 1 upon p summation of t square plus t Ct divided by 1 plus I t plus 2. So this is the formula for convexity what we have derived just now. Okay, this is the same formula what we have derived, okay, in the previous slide, right? So what is this convexity and how it will help us, okay, in our risk management, okay, or bond management, right? So it is basically a measure of the curvature or the degree of curve in the relationship between the bond price and the bond yield or the interest rate. Okay. So, convexity basically demonstrates us how the duration of the bond changes as the interest rate change. Remember that we use the first derivative to compute the duration, okay, and we will take the derivative of the derivatives to compute the convexity. So, essentially it will tells us, or it will demonstrate how the derivation or how the duration of the bond changes as the interest rate changes, right. So, when we will use it here, or how we will use the convexity? The bond manager, okay, or the portfolio manager use the convexity as a risk management tool, okay, as a risk management tool to measure and manage the portfolio's exposure to interest rate risk. Okay, so by knowing the convexity, a manager can identify, okay, what is the like a risk, or like what is the probability of a risky bond, or a or we will call like highly risky bond or less risky bond. Okay, so convexity is therefore a better measurement of interest rate risk. How far the price will change if any changes in the interest rate. Okay, so let us now compare this with the duration. Okay, what is duration basically? Recall that duration is a measure, okay, that it measures the change in the bond price when interest rate fluctuate. Okay, so it will measure, duration basically will measure the rate of change in bond price, okay, whenever there is a rate of change in fluctuate, or rate of change in interest rate or the yield. Okay, so if the duration of the bond is therefore high, it means that the bond price will move to a greater degree in the opposite direction of interest rate, right, because we know that there is an inverse relationship between price and the yield. Okay, the duration of the bond is, or whenever you computed that the duration is high, then it implies that the bond price will move to a greater degree in the opposite direction of the interest rate. So, the higher the duration, the larger the change in its price when the interest rate changes, and the greater is, greater its interest rate risk. So if you as an investor believe that the interest rate is going to rise in the future, you should consider bond with lower duration. Okay, so whenever any investor believes that interest rate is going to increase in the future, then they may consider the bond with lower duration. Okay, the convexity help the bond manager or the bond investor, okay, understanding the riskiness of the bond related to price. Okay, so convexity basically builds on the concept of duration, okay, and it produce a slope, right, because we have already seen that the second derivative is used here, so it basically produced a slope. Okay, so duration can be a good measure of how the bond price may be affected due to small and unexpected fluctuation. Whenever there is a small changes happen, okay, or small fluctuation, or any unexpected fluctuation in the interest rate happen, then duration can be a good measure. However, the relationship between the price and the yield is typically more sloped, okay, or typically more convex in nature, and therefore convexity may be a good measure which will give you the the uh, the relationship whenever there is a large fluctuation, or put it differently, that convexity is assumed to be a better measure for assessing the impact on bond okay, or impact on bond price when there are a large fluctuation in interest rate. So whenever there is a small fluctuation in interest rate, duration may be a good measure, but whenever there is a large fluctuation, okay, in the interest rate, then the convexity may be a good measure to understand the riskiness of the bond. Okay. So, as the convexity increase, the systematic risk, okay, to which the portfolio is exposed is increased. Okay. Systematic risk means the risk which is not diversifiable or undiversifiable risk. We understand this convexity very clearly here, by like understanding this diagram. Okay. See here, okay, we have two convex curve, that is for bond A and bond B, okay, and in the x axis we are measuring the yield, okay, or the interest rate, and the y axis we are measuring the price of the yield. Now look at here, okay, initially this should be the price, okay, that is called P star here, okay, and now we can see here that for bond A is more convex, right? This bond A is more convex than the bond B, okay. This means that other thing remaining the same, bond A will always have a higher price than bond B, okay. If bond A is more convex than bond B, then the bond price or bond A will always have a higher price. We can just see here that the other thing remaining the same. Suppose that, okay, like suppose that we are taking from here, okay, then we will see from here, okay, because this point is corresponding to bond A, so we will call like price, okay, of A, and here, okay, this point is corresponding to bond B, so we will call it as price of bond B. So essentially, okay, because the convexity, because bond A is more convex than bond B, the price of bond A is higher than the price of bond B. So this will give us one clear answer that why convexity is actually important. Okay. Sum it up and understand some of the rule of the duration. Okay. So the first rule says that the Macaulay duration of the bond is always less than or equal to its time to maturity n. Okay. So Dmac is always less than or equal to the time to maturity, that is n. We have already seen it, right. Equality of equality of these two will hold only for the zero coupon bond. So for the zero coupon bond, okay, the Macaulay duration may be equal to the term to maturity. Otherwise, okay, most of the time the Dmac is less than equal to n. Rule 2. Rule 2 says holding the time to maturity n is constant. When the coupon rate increases, then the Macaulay duration decreases, and when the yield to maturity or the interest rate decreases, the Macaulay duration increases, right. So there is an inverse relationship between Dmac and I. Rule 3 says for a level perpetuity, the modified duration can be computed as d modified is equal to 1 upon I being the yield to maturity. Okay. Rule 4 says that for a level annuity immediate of n payment duration, the modified duration can be computed as d modified is equal to 1 upon I minus n upon 1 plus I multiplied by 1 plus I to the power n minus 1. Okay. Rule 5 says the modified duration of coupon bond with coupon rate R, okay, and n maturity period and y yield to maturity, then the modified duration can be computed as d modified is equal to 1 upon I minus 1 upon I plus n time r minus I divided by 1 plus I multiplied by 1 plus I to the power n minus 1 time r plus I. Okay. And rule 6 says for a coupon bond selling at par, the modified duration can be computed as d modified is equal to 1 upon I time 1 minus 1 upon 1 plus I to the power n. So, the another way of risk minimization is the diversification. Okay. Diversification means that you will put your money in different assets or construct a portfolio in which you are going to invest so that your risk will be minimized. Okay, so rather than investing in one particular stock, you are now investing in different stocks or different bonds, or like some money in stocks or some money in bond, right? So suppose a portfolio of bond is constructed, okay, with the duration d1, d2 and up to dm, okay, and let the bond value be p1, p2, okay, and pt, so that the total value will be p is equal to sum of pj. Then we can define this weight as pj upon p at the weight of the bond j in the portfolio. Okay, so this weight is pj upon p. Okay, then the duration dp of the portfolio is the weighted average of bond duration can be computed as dp is equal to summation of wj dj. Okay, so if you have a two asset case, then we can just understand that, okay, the expected return of the portfolio can be computed as the proportion of money you are putting in asset 1 multiplied by the expected return plus the proportion of money you are putting in the stock 2 or the asset 2 multiplied by the expected return you are earning from that 2. That will give you the expected return of the portfolio. Okay, so I will take another class to explain you what is the portfolio, okay, and how the portfolio will help, or construction of portfolio will help the, or help to reduce the diversification. So the concept of diversification we will discuss in the next session. So we'll stop here today. See you in the next session. Thank you.